Hello, everyone. Good evening, good morning, good afternoon, based on your location. We hope you've had a good day and you, as well as your family and loved ones, are doing well and staying safe. On behalf of AIOUG, I would like to welcome you for our weekly webinar series. For those of you who are joining us for the first time today, AIOUG is All India Oracle Users Group, and we conduct our knowledge sharing webinars every Wednesday. We try and bring experts from all over the globe to help our community learn and grow. And so, today we are extremely delighted to have Maria Colgan with us. Maria is a distinguished product manager at Oracle since 1996. That's the time of 7.3 Oracle version. Her core responsibility is to advocate for Oracle database and the best practices for incorporating it into our environments. You probably have gone through her numerous blog posts and perhaps know her better as SQL Maria, the optimizer lady. And as you all know and are waiting for today, Maria is here to explain the explain plans to us. Now, before I hand off, I don't want to take too much of your time, but I want to remind you about a few things. First up, the presentation will be shared with all the attendees. Again, another thing we want to stress about is tweet post about today's webinar. In virtual conferences, that's the only way you'll be able to connect with all the attendees who are not only viewing from Zoom, but also from all our live streaming options. Yes, another point to add, in case you are not able to connect via Zoom, we also stream via our website. That would be aioug.org/live. And you can use the hashtags, hashtag AIOUG webinar and hashtag AIOUG virtual selfie to tweet and thank Maria for her time. And again, as I mentioned, use this opportunity to interact with all the attendees and take the discussion over to Twitter. And another important announcement, please use the Q&A panel at the bottom of your screen, and we will take the questions during the Q&A time at the end. With that, I would like to hand over to Maria. Maria, could you just share your screen and...
Yes, thanks so much for that lovely introduction.
Thank you.
So let me go ahead and share my screen. Hopefully you guys can see my slides now.
Yes, we can.
Awesome, thank you. So given the fact that we are a little tight on time today, and because I want to cover so much with you, because with the explain plan, there's always something else, some additional piece of information to share. I'm always learning new things when I look at new or complicated explain plans. So I want to jump right in. Now, there are 6 key topics that we'll talk about today. I'll do my best to get through all of them in the time we have, but don't panic if I don't get to everything. All of the slides are going to be made available to you and a recording of the session. So you'll be able to go back and listen to it, even though we will move quite quickly through the content. So I want to jump in and just start with the very basics. What is an execution plan? Well, what it is a series of steps or operations that the optimizer decides are necessary to execute your query. Now, each operation in the plan is going to do one of 3 things. It'll either produce rows, it will consume rows, or it will do both. So a good example of an operation that produces rows would be a full table scan. An operation that only consumes rows, so to speak, would be the final return to the end user, or like a group by, for example. But typically a sort, a group by, hash join, they will all consume rows, but also produce rows, send them to the next operation in the plan. Now, traditionally, when we look at execution plans, we see them in a tabular format or as a table. But actually inside in the code, the execution plan is always drawn as a tree. And by default, these are left deep trees that we're looking at, which means you start reading the tree from the bottom on the left-hand side. So in my example here, the very first operation in this plan is actually that full table scan of products. Now, the rows from that full table scan will flow up to the next level of the tree, which is the hash join. Now, a hash join, remember, consumes and produces rows, but in order to be able to produce those rows, it needs to join these rows from the products table to something. So, since it has nothing to join it to, the next operation in the plan will actually be the other input into that hash join. So, in this case, that's the full table scan of sales. Once the hash join begins to receive some of those rows from the sales table, it will begin doing the join and begin sending rows to the group by, which is, of course, the final step in that plan. So that's how the plan typically operates. And throughout the next hour or so, we'll look at all the different aspects of the plan, and I'll explain how you too will be able to understand exactly from a table how the tree is going to look. Now, along with the table of operations or steps needed to execute your query, you're also going to get additional information underneath that table. So, the first area immediately underneath the explain plan or the tabular format of your plan is the predicate information. This is where the where clause predicates you used in your query are divided into two categories. They're either going to be access predicates or filter predicates. Now, access predicates are predicates that help us retrieve the data. So they may be the stop and start key for an index, or it may be the row ID is being passed to a table scan. They're what we call access predicates because they're going to help us find the data we're interested in. And as I said, these access predicates are going to be listed underneath the plan. And if you look at the picture on the left-hand side there, you'll see that each of the access predicates, the line begins with a number. And that number corresponds to the entry in the table above where this where clause predicate will apply. Now, as I said, there's two categories: access, what we're looking at now, and filter is the second one. Filter predicates are where clause predicates that are not used to do the immediate data retrieval, but they're actually used to help us filter out rows once we start reading the data or once the data has been found. So these tend to be more non-equality where clause predicates, tend to fall into the filter category. And again, they'll appear immediately underneath the execution plan table. Now, below that, you also get something called the notes section. The notes section is going to give you detailed information about the optimizer features that may have been used. So, for example, if you are using the rule-based optimizer, which you know you shouldn't be using because it's been deprecated, that will be displayed in the notes section. If dynamic sampling kicked in because somebody forgot to gather stats, perhaps, or you're using a complex where clause predicate, then you'll see dynamic sampling in that notes section. You'll also see if you're using some plan management capabilities, so stored outlines, profiles, baselines, all that information also appears in that notes section. And starting in 19C, you get information about hints, which is incredibly useful. So you'll get information in the notes section about whether or not your hint was used, whether there was an error in your hint, so I spelt it wrong, or it didn't apply for some reason, or if it was simply unused because Oracle rewrote or transformed my query, making that hint no longer valid. So great, now we know what a plan is. How do I go about generating one? Well, there are lots of tools that we use day to day to manage and tune our systems that will display the execution plan for us. We use AutoTrace, SQL Developer, a SQL Monitor report, or even look at the trace files and use TK-Prof. But there's actually only two ways to generate the execution plan. You can either use the explain plan command that will show you the execution plan for the SQL statement without actually executing it, or you can look in $SQL plan, which is a dictionary view that was introduced in 9i that will actually show us the execution plan in the cursor inside in the shared pool. Now, if you've got very simple SQL statements, select something from employees or from department, very, very simple statement, no bind variables, chances are you will get the same execution plan from explain plan and $SQL plan. But under certain circumstances, the plans may differ. The most obvious one is if you use bind variables. Explain plan command does not peek bind variable values, and therefore it will not generate the same plan that you will get at runtime if you use the explain plan command. The other time that's coming to mind instantly with this is you won't get the same plan that you may get at execution with explain plan if you're using Oracle 12.2 or higher, and an adaptive execution plan is going to be used. So bear that in mind. There are some circumstances where the plan you get with explain plan is not actually the plan that finally gets used. So when at all possible, make sure you use $SQL plan as the way to view an execution plan to be sure it is what you're looking for. Okay, so how do I use both approaches? To use the explain plan command, what you're going to actually do is in front of your SQL statement, you'll say explain plan for, then it's your SQL statement, and the response back will be explained. So you won't see any results because remember, we're not executing the query, but you'll see the word explained. Once you see that, then you can go and look at the plan, which has been stored in the plan table. And you do that by selecting star from dbms xplan.display. Now that supplied package and that function inside in that supplied package actually takes 3 arguments. By default, you can run it with no arguments and you'll get the execution plan back. But if you do want to be very specific about it, if you do have a lot of plans in your plan table, then you may want to take advantage of the parameters. The first one is the plan table name. So unless you're actually very advanced and you're creating separate plan tables, it's simple to just leave that one to null or to the default. Then you can pass a statement ID. And then the third parameter is formatting. What information do you want to see in your particular execution plan? I'm going to spend a lot of time as we go through the presentation pointing out different values for this format parameter that you can take advantage of. I also have more detailed blogs about this and a YouTube video because the format is probably the most powerful parameter and certainly the most powerful tool you have to get a lot of information about what's happening in your execution plan. So stay tuned. I will talk about that more as we go through the presentation. Now, the alternative approach, of course, is to execute the query and then look for the plan stored in the cursor inside in the shared pool. And I do that by just executing the query. And then this time I'm going to query the same DBMS XPlan package, but I'll use a different function. I'm going to use the display cursor function, which again can take 3 arguments, but they are different to the just display function that we looked at a moment ago. With display cursor, the first argument is the SQL ID. If you don't specify it, then it shows you the plan for the previously executed statement in this session. The second parameter is the child cursor number. So for example, if I have a SQL statement that has multiple child cursors, there is the potential to have different plans for the different child cursors. So that's why the second one is the child number. And again, the third one is that format parameter, which I said is highly customizable. There are lots of different values. There's a link there to the Optimizer blog where we talk all about it. And of course, I have a video that shows you all the ways you can use it if you take a look on YouTube. Okay, great. So we know what a plan is. We know how to generate it. Let's move on now and start diving into what information is in that plan and how we can read and use that information. One of the most common questions I get is, what is cost? You have a cost-based optimizer. I see a column in my execution plan that's called cost. What is it and what can I do with that? Well, cost represents how much work or effort the optimizer believes is going to be necessary in order to complete your query. Now, the optimizer uses things like CPU and IO as the units of work it believes are needed to execute the query. So it is the estimated amount of CPU and IO needed for each operation, and then the total cost is for the entire statement, all of it together. You can see it, as I said, in the execution plan. There's a specific column called cost. And how important is it? How often do I, if I'm tuning queries, go looking at the cost column? To be honest, it's not that important to me. The only time it's important is when I'm trying to compare two plans. And this is the same reason the optimizer uses it. Remember, we have a cost based optimizer by default. That means it's looking to find the lowest cost plan for your particular query, because it's looking to optimize and use the least amount of resources to execute your query. And so, because of that, the plan with the lowest cost is by default the plan that's chosen. So I will only use cost if I'm comparing multiple execution plans. But otherwise, I don't do it. I certainly don't try and reverse engineer what the cost would be by trying to add up all of the numbers there in the column. First of all, they never, if your SQL statement is complicated, they're never going to add up the way you think they are. So I wouldn't worry too much or focus too much on the cost or how Oracle calculates it. The only reason you need it is to compare two plans to each other. What is the most important thing then in my execution plan? Well, it's the cardinality estimates. This is the estimated number of rows that the optimizer believes this operation in the plan will produce. And why is it so important? Well, it's going to influence all the other decisions the optimizer is going to make in the rest of the execution plan. So, how does the optimizer come up with these estimates? Well, these estimates are calculated using formulas that are based on the statistics we give the optimizer. So, if you didn't think gathering stats was important, let me assure you it's very important, because this is where they get used. They get used by the optimizer to come up with these cardinality estimates, or the estimated number of rows that will be returned by this operation in the plan. So, how are they determined? Well, let's look at a very simple example. Imagine I have a query that is selecting something from my table, and I have one where clause predicate that's an equality predicate on just one column in the table. Now, how does the optimizer estimate the cardinality for that? Well, in the simplest case, what it will do is it will ask, how many rows does this table have? Let's say the answer is 100. The next thing it asks is, how many distinct values are in the column used in the where clause? Let's imagine we have 5 distinct values in that column. Then the cardinality estimate is going to be 20. It's going to be the total number of rows in the table divided by the number of distinct values in that column. And therefore, 100 divided by 5, we get 20. Now, the more complicated your where clause predicates are, or the more where clause predicates you have, the formulas change. But it is all based on the statistics that we supply the optimizer. And again, the reason you need to care is because all of the other decisions the optimizer makes are based on these cardinality estimates. So, where in the execution plan do I go looking for these cardinality estimates? Well, they're there in the rows column of the table. So rows is what I need to go look for, but I can now see how many rows the optimizer believes or estimates are going to come back from each of the operations in that plan. But how do I know if the cardinality estimate is accurate? Well, remember, I can look at the predicate information underneath the plan, look at the corresponding line in the execution plan. So if I look down here and I see the number 6 in my predicate information, I can go to line 6 of the execution plan. That's a full table scan of departments. It estimates only one row is going to come back. And if I look at the where clause predicate, I could do select count star from the departments table where the department name equals sales and compare the result. Did only one row come back? Well, you and I know in this example, the answer is yes. Chances are we only have one department named sales. So that's a good estimate. But it's not always that easy. So I could do all of these count star queries for each of the predicates to try and estimate if I'm getting the right cardinality. Or I could cheat a little and I could add a hint called gather plan statistics to my SQL statement. And that will actually show me the actual number of rows returned for each of the operations in that execution plan. The gather plan statistics hint actually doesn't tell Oracle to record this information. It always knows how many rows have actually come out of each of the operations, but we don't normally persist that information in the cursor by default because it takes extra space, extra valuable space in your shared pool. So if you add the hint, what you're asking Oracle is, can you remember or can you record those the number of rows that are actually being returned in the cursor so that I can look at them afterwards? And how I look at that information afterwards is I change the format parameter in my DBMS XPlan display cursor call. And instead of just doing format basic or all, I actually change it to be all stats last. So when it returns the execution plan, it's actually going to look quite different. There will be additional columns appearing in my plan table. And the most important one is along with the original rows column that has been renamed E rows or estimated rows, I'll also get an A rows column or the actual rows returned by each of the operations. And by comparing the values in those two columns, I'll very quickly be able to see whether or not I got a good cardinality estimate or not. Now, if I don't get a good cardinality estimate, then I'm going to start looking at things like statistics and how my query is written to try and understand what's causing that problem. And I'll give you a cheat sheet of things to look for in just a minute. But for now, let's just focus on how we can tell we have a cardinality problem. So, as I said, we can compare the E rows and the A rows. But that works fantastic if I run queries that are serial. There's no parallel execution. But if I'm running a query with parallel execution, I may very well see a situation like this, where the E rows column has lots of information, but the A rows column only has information for the last two operations in the plan. So what happened? Well, if you're running parallel execution, what happens is the parallel server processes and the query coordinator share the same cursor. The last person to execute the cursor is the query coordinator. And that's what I've asked Oracle to show me. I've asked Oracle to show me all of the stats for the last execution of this cursor. Because all of these operations with zeros there were executed by the parallel server processes and not by the coordinator, I have no information for them. So how do I get that information to be populated? Well, I need to change the format parameter. Instead of it being all stats last, I need to change it to all stats all. Give me all of the execution stats for all of the processes that executed this cursor. Now, be very careful with this approach, especially if you're on a busy system where lots of people are executing these cursors at the same time or over time. The reason being is all stats last is accumulative. It will constantly add the next execution of that cursor to the running total. So your A rows may be way off from your E rows. This trick only works if the parallel executed query has only been run once. If you can't guarantee that, the only way you can get a good cardinality estimate is to take advantage of SQL Monitor. Now, the reason I don't do this entire presentation using SQL Monitor, because I do love it, it is a fantastic tool to help you when you're trying to read and understand execution plans, is it costs money. You need additional licensing to use SQL Monitor. You need to have the diagnostic and tuning pack license in order to use it. If you do have it, I strongly recommend that you take advantage of this. For many reasons, but the most important one being is that when you execute queries in parallel, the estimated rows and the actual rows are automatically displayed in a SQL Monitor report, and the A rows is accurately calculated just for this execution and not for previous execution. So you'll always get the correct answer. As promised, here's your little cheat sheet. What I've done is if you discover that your cardinality estimate is not accurate and you're trying to work out why, I've given you a whole list of reasons here and the solutions if you believe this is your reason. So, for example, are there missing or stale statistics? A good indicator of this is the fact that you'll see dynamic sampling level 2 was used in your query. You'll see that in the notes section underneath the table. Is there a data skew? In other words, by default, the optimizer is assuming uniform distribution of rows across the number of distinct values in a column. So if you know that one of the values in the column is far more popular than all the others, you may need a histogram in order to be able to share that information with the optimizer. As I said, the formula used for cardinality estimates gets more complicated the more where clause predicates you have on a table, or the more complicated the where clause predicates are. And so there are different techniques you can use, like extended stats, in order to be able to share more information about those scenarios with the optimizer so it can get the correct cardinality estimate. The same is true when you do joins. So the more columns you use in the join, the more the optimizer thinks that join is going to be very selective and will return very few rows. If that's not the case, then you need to give the optimizer more information and allow it to be able to get the correct cardinality estimate. All right. In the interest of time, I'll keep moving, but you've got the cheat sheet there in the slides, which will be shared with you. So you should be able to refer back to that when you're actually diagnosing problems. Let's move on now and talk about access methods. How do we access the data? And how many access methods does the optimizer actually have at its disposal? Well, you can kind of divide them into two categories. You can do a full table scan, or you can use some type of index access. And in fairness, the optimizer actually only has 9 access methods at its disposal. So what are those 9 access methods? Let's start with the obvious one. As I said, full table scan. Full table scan is going to read all of the rows in the table and filter out any rows that don't match the where clause predicates supplied in the query. It's typically used if there are no indexes on a table or if a parallel degree has been specified on that table. How does the parallel degree affect cost? Well, let's imagine a full table scan costs 100. If I put a parallel degree of 4 on that table, then I can reduce the cost from 100 to 25. Why? Because a parallel full table scan takes the price or the cost of a serial scan and divides it by the parallel degree specified. So you can make a full table scan much cheaper by specifying a larger parallel degree on that table. Okay, so that's full table scan. Next up, we'll do table access by row ID. What this means is that somebody has specified a row ID either in the where clause predicate, or we got it by looking up an index. And we're going to use that row ID to retrieve the necessary rows from the table. So what is a row ID? A row ID specifies the data file, the database block within that data file, and the row location within that block that we're interested in. So that's what a row ID is. And as I said, it's either passed directly in the where clause predicate or we get it via an index lookup, but it will allow us to then go to the right spot in the database block and pull out the row that we want. Index unique scan is probably the most popular execution plan we want because it tends to be the most efficient. Because it will only return one row. And it's used only, however, when I have a unique index or a primary key index constraint to guarantee this one row will be returned. And it's only used if I then have an equality predicate on that primary key or on that unique key. What's much more common is an index range scan. An index range scan is going to access the adjacent index entries and return row ID values for those entries. And it's going to be used if I have an equality predicate on a non-unique index, or if I have a range predicate on a unique index. So perhaps I have a between, less than, greater than type of query, then even on a unique index, I'll get an index range scan. An index skip scan is the next access method we're going to look at. With an index skip scan, it's going to be used if I have a multi-column index and the leading edge of that index, so the first column in the index, is not actually needed in my query, and the number of distinct values in that column is not very high, where the number of distinct values in the subsequent columns in that index are really high, and so it may be worth the effort to skip over that initial value and use the other column values in that index to answer my query. That's an index skip scan. A full index scan is going to process all of the leaf blocks in an index, but it's not actually going to process all of the blocks in the index. It's only going to process as many branch blocks as it needs to find that first leaf block. And it's used when all of the necessary columns for a query are in the index, and oftentimes when the order by has the same order, the columns in the same order as the index itself. A fast full index scan, on the other hand, is going to access all of the blocks in the index, and it's effectively going to replace a full table scan in queries where all of the columns I need from this table are present in the index. And I'm able to use multi-block reads for this, so it's a more efficient access of all of these index blocks. And it's the only index access method that can be parallelized without requiring partitioning. So it can be quite useful in scenarios like that. Index joins. Index join is where I typically have a very wide table with lots and lots of columns in it. And in my query, the columns I'm interested in are present in two or more of the indexes. And by scanning those indexes and then hash joining the results of those scans, it's going to be more efficient than reading that giant table because it's very wide and perhaps lots and lots of rows. So we'll do an index join where we'll read two or more indexes instead of the table to pick up all of the columns that we need, and then we do a hash join to get the final result. The final access method, excuse me, is bitmap indexes. Bitmap indexes, instead of storing the value and the row ID as we would typically do, we store a bitmap, which is typically zeros and ones, a very efficient way to store information, with each as the key value. And then there's a mapping function that will convert each bit to a row ID. Now, we typically use bitmap indexes in data warehouses, especially if I'm trying to get a star schema transformation going. What each of the reason they're so useful is that I can do a lot of and or logic on multiple bitmap indexes, merge them together, and come up with a final set of row IDs that need to be retrieved from that table, making it quite an efficient execution path in that scenario. So let's go back, because we're going to keep looking at this same execution plan over and over again throughout the course of the next hour or so. And so I'm going to ask you, where in this plan would you find the access methods? Which column tells me where the access methods are? Well, they're present there in the operations column. And what if the access method I'm getting is not what I want? Maybe I don't want all those full table scans or table access full that you see there in the plan. Well, if that's the case, I'm going to do two things. I'm going to check to see if there's an alternative access method. So is there an index that could have been used? And if there is, then I'm going to look at the cardinality estimate, because that will influence greatly the optimizer's choice of access method. So you've seen all the access methods. I want you now to pretend you're the optimizer and have a look at a query and tell me what access method you'd use. So we're going to be looking at the customers table. The customers table contains 10,000 rows and it has a primary key index on the customer ID. We're looking at a query now that's selecting the country ID and the name from our customers table, where the customer ID is in 100, 200, or 100,000. So I have a non-equality predicate on a primary key index. What access method do you think the optimizer would choose? Well, if you said index unique scan, you'd be correct. And now you may be thinking, hang on, Maria, you just told me I couldn't use an index unique scan if I had a non equality predicate in the where clause on that primary key. And you're right, by default, you can't. But in this case, the optimizer has helped you out and it's rewritten your query using an or predicate instead. Because there were only 3 elements in your in list, the optimizer rewrote the query to say where the customer ID equals 100 or the customer ID equals 200 or the customer ID equals 100,000. And by rewriting your query like this, we were able to do an index unique scan on that index. What about this case? Same customer table, same primary key index. Again, a non-equality predicate. This time it's a between 100 and 150. What access method do you think the optimizer is going to choose? Well, if you said index range scan, you'd be correct. Why? The same trick we used before can't be used here. The optimizer doesn't know all of the values you have in your particular table between 100 and 150. So it has no way of rewriting the query and guaranteeing it'll get the exact same results that this query will return. And so from that perspective, even though we've got a primary key index, we can't do an index unique scan. We're going to do an index range scan. So hopefully that makes sense why we would take the approach that we did. Now that you know there are only 9 access methods available to the optimizer, hopefully it'll make it easier for you to understand why the access method that you got was chosen and what you may need to do in order to get the access method that you want. Some of the big issues with access methods, again, for each section, by the way, you'll get one of these cheat sheets. So let's look very quickly at what some of those issues might be. Well, you may be using a table scan instead of an index. Remember the trick I told you that if somebody puts a parallel degree on a table, that would reduce the cost of the full table scan. And if that parallel degree is high enough, it may suddenly make the full table scan cheaper than the index access. So be very careful. If you're using parallel execution, you're putting parallel degrees on tables, it may alter the execution plan, not for the query you're working on, but actually for other queries because you're changing the cost of the full table scan. Another thing you should never do is change the value of a parameter called db multi-block read count. This parameter, if it defaults, works just fine with the optimizer. It uses that information to calculate the cost of a full table scan because it's able to read multiple blocks from that table in one IO operation. If you start monkeying with that or changing the value of that parameter, then what will happen is you will be actually changing the cost of a full table scan. And if you do that, then you have, again, the potential of getting a full table scan instead of an index access. So please do not change the value for the DB multi-block read count. Let it default. Let the optimizer use its standard cost model for full table scans. What is normally much more common, though, is what I call index confusion. There are multiple indexes created or specified on a table, and the optimizer is picking the wrong index. Why might that be? Number one reason, stale or missing statistics. The cardinality estimate is wrong, and so the optimizer has chosen the wrong index. Another reason is the cost of a full index access sometimes is cheaper than doing an index access followed by a table access by row ID. In other words, the optimizer will nearly always pick the index that has all the columns it needs, even though it'll need to do a full index scan on that index, rather than doing an index range scan or an index unique scan and then having to go back to the table to pick up the additional columns that it needs. So be careful of that. You will find the optimizer will lean towards the index that has all the columns that it needs. As I said, the last point there, pick the index that matches the most number of columns that it's after. Okay, great. So we looked at cardinality estimates and we looked at access methods. Let's talk a little bit about joins now. How many join methods do you think the optimizer has? Well, if you think it's more than the access paths, I'm afraid you're wrong. The optimizer really only has 3 join methods at its disposal: nested loop joins, hash joins, and sort merge joins. So let's talk a little bit about each one of these and when they're used. Nested loops joins are typically used when the 2 tables that I'm joining together are quite small. And if you're familiar with how you write code, a nested loop join is basically an embedded for loop. So for every row in the outer table, we'll scan through every row in the inner table looking for a match, like an embedded for loop. And as I said, it's typically done when the tables are small. And if I have a good mechanism for looking up the matches in that inner table. So in other words, if I have a index that I can use to probe into that smaller table on the inside to see if I have any matches for each of the rows on the outside table. A hash join is slightly different. It is normally done when I'm joining larger tables together. And how it works is this: we start on the left-hand side of the join by scanning the smaller of the 2 tables, and we'll apply any where clause predicates we have to that table, and we'll get a set of results out. Those results will be brought into memory, and a hash function will be applied to the join column. And we'll use the results of that hash function to build what we call a hash table in memory. We'll then go over and scan the table on the right-hand side of the query. Again, we'll apply any where clause predicates we have for that table, and the resulting rows will then be passed into memory, and the same hash function will be applied to the join column, and we'll use that value to probe in or look into the hash table and complete the join. Now, hash joins, as I said, are normally done when there are larger tables and when there's an equality predicate for the join. If you don't have an equality predicate, you're not going to get a hash join. Sort merge joins are often done when the join condition between the 2 tables is a non-equality predicate. And normally it's chosen if one or both of the inputs into that join are already sorted on the join key. Why is that? Well, in order to do a sort merge join, it's actually a 2-step operation. The first step is to sort the inputs of the join on the join key. So as I said, if you already have perhaps an index, with the leading edge of the index being the join key, then it's already sorted the data on that join key for us. And once you have those 2 sorted lists, so from each table, sort the input to the join on the join key, then we simply merge those 2 lists together, and that is the result of the query or the result of the sort merge join. So as I said, there are only 3 join methods, but there are multiple join types that can be used in your queries. So traditionally or typically, we use inner joins. So only return the rows that satisfy the join condition. So I only want the intersecting rows between my 2 tables. But there are other types of joins. You can use outer joins, and they might be left outer joins, right outer joins, or full outer joins. And with outer joins, what you're telling me is I want you to return that intersected set of rows, so the set of rows where there is a match for the join, but I also want you to return the rows from the table that I've specified, even if there is no match. So depending on whether you use ANSI syntax or whether you use Oracle syntax, if you're going with the traditional Oracle syntax, it'll be all the rows from the table without the plus sign. So in other words, all of the rows from the table where even if we don't have a match, I want all of those rows back too. Full outer join, it can also be a Cartesian join. And what that is I'm joining every row from the table on the left to every row on the table on the right. Now, typically, this is only a good idea if I have very small tables, or I know for sure one of the tables is very small coming into the join. If I see a Cartesian join being used in an execution plan where I'm not expecting it, where maybe the tables are quite large, that's an indicator to me that I wrote my SQL statement. Why? Because a Cartesian product is only going to be used by the optimizer if there is a missing join predicate in my query. So it will use it sometimes if the volume of data is very, very small. But typically it shows up in more complicated queries where I'm working on a big data set only if someone has forgotten one of the join predicates in that query. And I've got a table accessed in the query, but has no join predicate to it, then the only option the optimizer has is to join all of the rows in that table to all of the rows in the current result set. So be careful of that if you see it show up in the plan. Semi-joins and anti-joins only show up if you've got subqueries in your query. So in other words, you have the main body of your query, then there's a where clause predicate, and then one of the predicates is equal to or in, and then you have another query, another select, dot, dot, dot. So if you use those types of queries that have subqueries in them, and it's an exists or an in predicate that's being used with that subquery, then you'll get a semi-join. In other words, only return rows from the outer table where there is a match with this subquery. The reverse is true if you're using a subquery with a not exists or a not in. Then you get an anti-join. And what it means is only return rows from the outer table when there is not a match in this subquery. Okay, so they're your join types. Each of these join types, by the way, will use one of our join methods. But the join types will be predicted or dictated by the way you wrote your query. The join method is the optimizer's choice. So let's take a look at our execution plan. Where do we find the join methods that are being used? We find them right there in the operations column of the plan. And if I'm getting the wrong join type, the very first thing I do is I check to make sure the SQL statement was written correctly, and I do have all my join predicates specified. If I do, and I'm still getting the wrong join type, then I start looking at the access methods and the cardinality estimates, because again, all of those will influence the join, as will the statistics. So I'm going to go back through all the steps we've already looked at and use those to help me determine whether or not I'm getting the right join method. And if not, how can I get the right one by fixing those other steps in the plan? Okay, so now let's have an opportunity to pretend we are the optimizer. Here's the query you're looking at. It is a join between employees and departments. The employees table has 107 rows. The department table has only 27 rows. And there is a primary key, foreign key relationship between employees and departments on the department ID column. And so I'm asking you, there is an equality predicate between employees and departments on this department ID. What join method should you use if you were the optimizer? Well, given the fact that the tables were small. We had an equality predicate on the primary key, foreign key relation column. Then, if you chose nested loops, you'd be correct. What the reason I'm saying that is, remember, it's the for loop operation in this. So for every row, I want you to for every row in the departments table, I want you to use the index to look up the department ID in the employees table. And so that's what we're using here. That's why we chose a nested loops. Now, from 11G onwards, you'll notice that the nested loops, it doesn't appear as a single operation in the plan anymore. Oftentimes, you see it as two entries in your execution plan, two operation IDs attached to that one nested loops. And the reason for that is we actually put an optimization in 11G where we want to batch up the row ID lookups so that we don't keep trying to read the same database block over and over again. If we batch up the row IDs and we look them up all together, we can do it far more efficiently and with far fewer IOs. So the first nested loops you see there in the plan, the one on row 2, that nested loops is the join between the departments table and the employee department index. And the second one that's there on line 1, that's the actual batch lookup of the row IDs we got from the index for the corresponding rows in the employees table. So just so you know what's going on. So don't be afraid if you're moving from older versions of Oracle, you're going to hopefully 19C now, which is the latest long-term support release of the Oracle database. If you see some plan changes that normally would make you concerned as part of an upgrade, don't be concerned if it's coming from an older version and the only change is that second nested loops operation. All right, let's move on now and look at a different query. This time we're joining orders and order items together. Tables are a little bit larger this time, 105 rows, 665 rows. There is an equality predicate on the order ID column. What join method would you use? Well, I gave you a hint. There's an equality predicate, slightly larger tables. It's going to be a hash join. Pretty straightforward. 2 full table scans followed by a hash join. If you're worried that you're getting the wrong join method, as I said, you want to be looking at cardinality estimates and access methods. But what may trigger that? Well, we may get a nested loop selected instead of a hash join if we have a cardinality misestimate on the left-hand side. In other words, we think the number of rows coming out of the table on the left-hand side is actually very small, when in fact it's going to be much larger. That's typically done with the cardinality misestimate on the table on the left-hand side. So go back to the previous guidance I gave you on how to get the correct cardinality estimate. If you fix that estimate on the left-hand side, you should automatically get the hash join. If a hash join is being selected instead of a nested loops, then this can be more difficult to fix because the optimizer is not taking into consideration some of the caching benefits it may get by batching those row IDs together and doing a single block lookup. But the good news is that's going to be automatically fixed, both of those cases. I got a nested loops instead of a hash join. I got a hash join instead of a nested loops. Both of those should be addressed by taking advantage of adaptive execution plans that came with 12C. And what it's going to do is it's not actually going to make the final decision about the join method until we're in the middle of the execution. So until it sees how many rows are coming out of the table on the left-hand side, it will delay making the decision about the join type. If the number of rows coming out of the left-hand side is very small, it will use the nested loops approach. If the number of rows coming out of the left-hand side of the join actually turns out to be very large, it will choose the hash join. And it's able to do that because starting in 12C, we can basically calculate both plans and store both inside in the cursor and make the decision on the fly. So we'll actually have a lot of extra operations in the plan table, but we'll make the decision on the fly on that first execution. Once the decision is made, we'll stick with that plan. And those additional operations become no ops or null operations. They don't cost anything. They're just there as a just in case. But we didn't use them, and so we will never use them going forward. But they're there just in case we want to change our mind. You'll also see a new entry in the execution plan called a statistics collector. And that collector is there to buffer the rows coming out of the left-hand side so we can work out how many there really are, make that final decision between hash join nested loops. Once the decision has been made, that stats collector again becomes a no-op or a pass-through operation. It has no impact on the query performance after that initial execution. All right, let's move on and talk about the join order, which is one of the more complicated things to often derive when you're looking at the execution plan in a tabular format. So, what is it? Well, the join order is the order in which the tables are joined together when I'm using a multi table statement. And the optimizer has one goal when it comes to the join order. It's looking to reduce the number of rows as soon as possible inside the SQL statement or inside the execution of the SQL statement. Now, the reason for that is we want to reduce the number of rows we need to carry from one operation to another operation. We call that the result set. And we want to reduce the size of that result set, ideally, so we can always keep it in memory and we never have to spill to disk. Now, if I need to spill to disk, if my result set is too large and I don't have enough memory available for it, where does it go? It goes to the temp table space. And that means I need to waste resources writing it to the temp table space and waste more resources reading it back from the temp table space when I'm ready for it. So, as I said, the optimizer has a very strong goal of reducing the number of rows as quickly as possible when it's executing a SQL statement. So, there's some basic rules that always apply. So, for example, if we know in our SQL statement, even though I've got multiple tables in that SQL statement, if I know for sure that one of the joins will return at most one row, that join always goes first. So, for example, if I'm joining two primary keys together and I know at most there'll be one match for those, it's either a match or it's not, there's no match, that join will go first. So, if I can guarantee that I'm only going to get one row with an index lookup, primary key index lookup, then that's going to go first. The way I write my queries also can influence the join order. So if I use outer joins, then I'm forcing Oracle to access the tables in a certain join order. So with an outer join, I need to use the table with the outer join operation second after the other table. Why? Because not only do I need to do the join and return the results of the join where there is a match. So I need to return all the rows where there is a match, but I also need to return all the rows where there isn't a match. And so that table needs to go second so I can do the join and also take all the rest of the other rows with me to return to the end user. So the order, like if you do an outer join, you're forcing a particular join order for the optimizer. The same is true if we use views inside in our queries. Now, by default, the optimizer is going to try and do something called view merging, where it takes the definition of your view, so the SQL statement that makes up your view, it inserts it into the SQL statement we're looking at, and it tries to optimize it as a whole. So it looks at all the different potential join orders between the tables in the view, the tables outside the view, all of that is considered. If for some reason the optimizer cannot do view merging in your particular query, in your scenario, then the tables used in the view definition need to be joined together first, and the result of that view determined, and then the result of that view joined to the other tables in the outer query. That will force a particular join order because we cannot do the view merging. So if I'm looking at my execution plan, how do I know, or where do I see the join order? Well, unfortunately, there isn't a single column in the table that's going to show you the join order. It doesn't appear that way. And I've heard a lot of rules about how to determine the join order from an execution plan. They don't always work all the time. And so I'll give you the basic one now, but I'll also show you in just a second the foolproof way to know what the join order actually is. That's quite useful if you've got more complicated SQL statements. To determine the join order, we need to look in the operations column of the table. We need to start at the top of the table and we need to work our way down through the different operations in the plan until we find the first operation that only produces rows and doesn't consume any rows. So if we look at the first step in the plan, that's the select statement, so that's now good. Nested loops produces and consumes rows, so that's not it. Nested loops produces and consumes rows. That's not it. Third nested loop. That's not it. Fourth nested loop, hash join. That's not it. Fifth, merge join Cartesian. Again, still produces and consumes rows. Sixth step, table access full department. That could be the first table in our join order. And then I continue to go down through the different steps in the plan, looking for those operations that produce rows, and that should give me the join order. But as I said, query transformations, the indentation of the plan can often be confusing. And if I've got pages and pages that make up the execution plan, it's nearly impossible to find that join order. So I'll show you a little cheat that I use on how to do it. When I'm asking Oracle to show me the execution plan, I'll often add an additional predicate to the format column. I add a plus outline. What that does is it gets Oracle to produce the complete outline or the complete set of hints needed to reproduce that SQL statement. Excuse me. And one of those hints is actually the join order. It's under a hint called leading. The leading hint will show me the exact join order for my query. So in this case now, it does take a little bit of not expertise, but a little bit of patience to be able to read or understand what this hint is telling me. So the leading hint tells me that the table with the alias D, or in my case, departments, that's the first table used in the plan. It joins to the E table, that joins to the E table again, that joins to the J table, that joins to the D table. Now, you'll see my query in a minute and you'll understand why I keep joining back to the same tables over and over again, but you at least get the aliases in the right order. And if you're clever with the table aliases you use in your queries, it should be very easy for you to dictate or determine the join order for your table, or sorry, for your query. So what can cause my join orders to be incorrect? Well, again, we go back to the previous operations in the plan. So I look at the cardinality estimates for the individual tables and for the joins themselves. That will guide the join order because, as I said, we're looking to reduce the volume of rows being returned. If the optimizer thinks a join is going to be very selective, i.e., it will return very few rows, then it may go first when really it shouldn't, because the cardinality estimate for that join is wrong and it will actually return a lot of rows. So get your cardinality estimates correct for the single table operations. For the joins, the join order should pop out correct by default, so to speak. Okay, now I know a lot of people only have an hour, so if you need to drop off and get on with the rest of your day, thank you for joining us. We are going to spend just the next 10 to 15 minutes quickly going over partitioning and parallel execution before we'll take a break and look at the Q&A. I know there folks have been asking questions via the Q&A option in the webinar, and we will get to those before we wrap up today. So let's talk a little bit about partitioning. Partitioning, remember, is going to allow us to take a very large table inside in the Oracle database and break it up into separate partitions. And by dividing the data this way, it's going to actually be much easier for us to manage because each partition is going to be its own physical structure or its own physical object inside in the database. But there's also a performance benefit from using partitioning because we can take advantage of something called partition elimination. In other words, the optimizer understands the partitioning structure of a table and can utilize that to access only the partitions we need to scan to answer our particular query. And what's great about partitioning is you don't need to change your application to be partition aware. You can take a table that was traditionally just a regular heap table inside the Oracle database, and you can, while the application continues to run, transform that table into a partition table and start to take advantage of partition pruning. So, how does it work? Well, let's imagine I have a sales table inside of my database and I've partitioned it on the date column, the sales date column, and each day is a separate partition. When the query comes in, as you see it here, I have said I want to find the total amount of sales we made for the long weekend in February. And that long weekend is 3 days, February 10th, 11th, and 12th. When that query comes in, instead of reading all of the rows in the sales table, partition pruning can kick in and I'll access only 3 of the actual partitions, the Friday, Saturday, and Sunday of that long weekend. So reducing the volume of data that needs to be read, making the query much more efficient. Now, there are 2 types of partition pruning that can happen. You can get static pruning. In other words, the optimizer knows when it parses the query exactly which partitions it's going to access when it executes that query. Or you may get dynamic pruning. In other words, during the parse operation, the optimizer knows that when it executes, it probably won't need to read all of the partitions, but it doesn't know yet what partitions it will read. Now, typically you get dynamic pruning because we don't have a where clause predicate directly on the partition column. We have a join on that partition column, and we'll get the elimination via the join. So let's take a look at this in action. Where do I see partition pruning in my plan? Well, I'll see it in the P start and the P stop columns. That indicates which partitions in the table will be accessed. If you see the same number in both the P start and the P stop column, that indicates that I'm getting just one partition. If you see different values in P start and P stop, then that tells you the range of partitions that you are going to need to scan. If you see the word key in the P start and P stop column, then that indicates that you're not getting static pruning, but you're going to get dynamic pruning, and we'll get the pruning via the join key, hence the word key appearing, and that's how we will do the pruning. So when you look at the P start and P stop column, even for a simple table that only a simple query that only has one table, I still see a lot of values in the P start and the P stop column. Well, what does that tell me? What are all these numbers? What do they mean? The numbers dictate the numbering or the unique identity of each of the partitions in the table. So what we saw there is an example of a table that is not only partitioned, but it's also sub-partitioned. So each of the partitions has been broken down into additional smaller pieces. And each piece has a unique identifier, which is what all those numbers are trying to show us. So let's start with the basics. I have my table here. It's range partitioned by date, and each of those partitions is given a number. And I have 10 partitions in my table. So each one, February 5th is partition 1, February 10th is partition 5, and so on. So there are, I'm not showing you all 10 here, but you get the idea. So each partition is numbered from 1 to n. And in my example here, n is 10. Now, within each of those partitions, each subpartition is also numbered, and they're numbered 1 through m. And m in my example here is 2 because I just have 2 subpartitions in each one of these. Okay. Finally, each physical object or each physical uh, heap table or object that I'm storing gets a number. And that number is 1 through n times m. So in this case, because n is 10, m is 2, that's 1 through 20. So in other words, each physical object gets a unique identifier from 1 all the way through 20. So if we look at the execution plan, what all these numbers actually mean, well, 10 is the overall partition number that I'm accessing, which is range partition 5, sub partition 2. So that's what all of those numbers actually mean. It's giving me that unique identification of which partition is being scanned. Now, as I said, partition pruning can happen statically, as we just saw, because the where clause predicate is directly on the partition key column, or it can happen dynamically because I'm actually going to get the join predicate on that partition column. So in this example, we're joining sales and time together on the time ID column, which is our partition key column. But the where clause predicate is not on the sales table. It's not on the partition key. It's actually on the other side of the join. So that will be a dynamic partition pruning because we'll know that we're going to get partition pruning because we have a where clause predicate that's going to help reduce the number of time IDs coming into the join, but we don't know what they are until we get to query execution time. And so we'll see in the execution plan the word key inside the p start and the p stop column for the sales table because it wasn't the one with the where clause predicate. So in our bigger query, as I said, we're going to identify p start and p stop columns will give us this information about partitioning. Now, if we see the word key there, we know it's dynamic. If we see numbers, then we know it's static pruning. But what does that BF000 that shows in the plan mean then? Does it mean dynamic pruning? Does it mean static pruning? What is it? Well, it's actually an optimization called Bloom filter pruning, yet another type of pruning that we can get. And Bloom pruning typically happens when I'm doing a hash join between two tables. So we start by scanning the smaller of the two tables. We'll apply any of the where clause predicates we have on that table, and the resulting rows will flow into the hash join. And the hash table will be built in memory. But at the same time, we're actually going to create a Bloom filter. Now, a Bloom filter is a bit like a bit vector. It is, in fact, a bit vector. It has zeros and ones stored in it, and the position of the ones indicates which partitions need to be scanned from our transaction tables. So 1 is an absolute partition, 0 means skip the partition. So the first two partitions in the table will be scanned, the third and the fourth will be skipped, fifth and sixth will be scanned, the seventh will be skipped, and so on. And that bit vector of partition numbers will be sent down to the scan of the transaction table. So we'll only scan the partitions that the bit vector tells us to. And what that'll do is then help us to very quickly eliminate unnecessary IO, and only the partitions that need to be read for the query will be read, and the results sent to the hash join. So it actually makes it much, much more efficient for us to be able to do the join predicates. It makes it much more efficient for us to be able to do the hash join. So I'm just looking at the clock. I'm going to very, very quickly do parallel execution because we only have 5 minutes left before I need to jump over and do Q&A. So let's quickly jump in and talk about parallel execution. Now, typically when we connect to the Oracle database, we get a session or a process that does all of the work that we're asking of the Oracle database. It's going to execute our queries. But if we execute a query in parallel, then that process becomes what we call the query coordinator. And it isn't actually going to do all of the work to answer our queries. What it's going to do is it's going to retrieve processes from a pool of shared resources, and these processes are called parallel server processes. And it is those processes that will actually do the work to answer our query. Now, the query coordinator communicates with these processes, and these processes communicate with each other via in-memory buffers. That's how they're going to communicate. They'll pass data around to each other. And as I said, the parallel query processes will do the majority of the work. The coordinator will simply tell them what to do, take the results from those processes, and return them to the end user. So how does it work? Well, let's imagine we've been asked to find the maximum amount of goods we've sold where the ship mode equals air. And let's say we have a parallel degree of 4. That means the query coordinator will get 4 parallel server processes from that pool of shared resources, and it will tell those processes they need to scan the sales table. So each one of the processes will scan a different part of the sales table. They'll apply the where clause predicate to its group of rows. It will calculate the max amount sold just for their group of rows, and then they'll return the results to the query coordinator, who will get 4 max sales amount. And the coordinator will then simply aggregate those amounts up to find the total, the highest max, and return that to the end user. How does that look in the execution plan? Well, it's pretty easy. The first thing you need to do is find where the query coordinator wrote its name in the plan. The query coordinator always puts its name in the plan, and typically that indicates all of the operations above that line in the plan will happen serially because they'll be done just by the query coordinator. And typically it's very little work because the query coordinator is very lazy and doesn't want to actually do any work. So in this case, it just does the final aggregation to find the max and returns the result to the end user from the 4 results it got from the parallel server processes who did the majority of the work in the plan. So you see there, they did the full table scan of the sales table. They did the initial max for each one of their pieces of the sales table that they returned to the query coordinator who did the final aggregation. Now, how do they divide the work? How is the sales table divided up among all these parallel server processes? Well, Oracle is going to divide the work up using one of 2 methods. So each of the objects that need to be accessed are divided into what we call granules. Again, the goal of this is to balance out the work to make sure each of the parallel server processes does their fair share of work. Depending on the structure of the object that's being scanned, we'll either do a block range. So in other words, the first parallel server process is told it's going to scan block 1 through 4. The second one is scanning block 5 through 9. The third one is scanning block 10 through 13, and so on. They're given these ranges of blocks that they need to scan. Once they finish working on their first granule, they may get a second one, and so on until all of the data has been scanned. If alternatively the object is partitioned, then and depending on the where clause predicates that are being used, each parallel server process may not actually get a range of blocks to work on. It may actually just get its own partition to work on. And again, that decision of how the data will be distributed is made by the optimizer. And you'll see it in the execution plan because it appears in the operation right above the either full table scan or in fast full index scan, whatever it may be, you'll see the distribution or the granule breakdown in the operation right above that in the execution plan. Which access paths and how they're parallelized? I've given you a cheat sheet here where I've given you the list depending on whether it's a partitioned, non-partitioned table, and the indexing. Because remember, most index accesses cannot be parallelized unless it's happening on a partitioned object. The other thing that you'll notice too is oftentimes it's not just one set of parallel server processes that get allocated, but two. So in this simple example, I have the same query against the sales table, but this time, instead of it being a max, I've got a sum, and I'm looking for the revenue by product. And so I'm doing a group by on the product ID. And so in this case, there will be two sets of parallel server processes requested from the pool by the coordinator. One set that we call the producers, who will do a lot of the scanning of the initial data, and the consumers that are going to do the aggregation. Now, when the query coordinator asks for two sets of parallel server processes, he'll get 4 in each set. So there'll be 4 producers and 4 consumers, even though the parallel degree was 4, 8 processes are actually going to be working. So what'll happen here is that the producer processes, those query processors, are going to scan the sales table. Again, it'll be broken up into granules automatically for them. Each of them will scan their particular set of rows, apply the where clause predicate to them, send the results to the consumers. The consumers will then begin to do the sum, or the sum of the revenue. And once they complete, they don't get any more rows from the producers. They'll send the answer or their sum to the query coordinator, who will then sum up those 4 results and return the answer to the end user. So giving you an idea of what happens when you get a producer and consumer style execution plan. Now, as I predicted, we did very well. We got through a lot of material, but we have run out of time. I do want to spend the last 10 minutes addressing your questions. But as we said before, and let me just scoot down, all of the slides that we had, they are they're already shared. I've already given them to the user group. You can get more information on the Optimizer blog on SQLMaria.com, and also on my YouTube channel about how to read execution plans. And what I'll do is next week, I'll post a video that finishes the parallel execution section so that you have access to that as well. So you won't have missed anything at all. So with that, I'd like to invite one of the organizers, if they want to help me out with the Q&A, if they've already read through them, or I can read them quickly and try and address them. I don't know what you prefer.
Yeah, hi Maria. So you can see there are 15 questions.
Okay.
It's better you pick the questions because some of them maybe it's a bigger one.
Okay, fair enough. Let me quickly try and go through them then. So one of the quick first ones that I see that'll be easy for me. When does table access storage full? First rows will be seen in the explain plan. When does the table access storage full first rows be seen in the plan? So let's talk about table access storage full first. So table access storage full indicates that this query is being executed on the Exadata platform, and that query offload is going to occur. In other words, the database server is going to push the query down to the storage cells that have database specific software on them that will allow them to scan and filter the data down on the storage tier as part of the full table scan, and only return the rows where we have a match, and only the columns that we need from those rows to progress the query. So that's what table access storage full means. Table access storage full first rows is an additional optimization where we're using the first rows optimizer mode. In other words, I've said to the optimizer, I don't want you to optimize this query for for all the rows, which is the default. So the default is the optimizer assumes all the rows are being returned for the query. First rows n, where you give me a value. By the way, first rows is no longer supported. It's been deprecated. It needs to be first rows n. You need to tell me how many rows you want. Is it 10, 20, 50, 100, whatever it may be. very commonly used for applications that use pagination. In other words, they only show the first part of the result to the end user. The end user normally clicks on one of those entries and never goes and looks at the rest of the results. So we call it first rows. And that's when you would see that entry in the plan. Excuse me. All right. Should we gather statistics on objects every day? What is the best practices? Oh, Annika, that is a full session in itself on what are the best practices for gathering stats. Do I need to gather stats every day? That really depends on your workload. What you need to give the optimizer is a representative set of statistics for your environment. It doesn't have to be up to the minute, they just need to be representative. So it's okay for the stats to say there are 10,000 rows in the table when really there are 10,500 rows. It's not okay for the stats to say to the optimizer, there's one row in this table when really there's 500 rows in this table. Why? You want the statistics to be at least the right order of magnitude. So hundreds of rows if there's hundreds of rows, thousands of rows if there's thousands of rows, and so on. So you need a representative set of stats. When they should be gathered and how frequently will depend on your workload. If your data set is very static, there's no need for you to gather stats every day. If, however, your data set is very dynamic, you're constantly inserting, updating, or deleting rows, then you may need to gather stats every day and maybe even more frequently than every day, but perhaps not for every object. So it is very dependent. I'm sure, can coordinate a session with Nigel, the optimizer product manager, to give you best practices for gathering stats session, because that might be more useful than what I can tell you in just a few minutes. Real time when we do use bitmap indexes. Okay, so there is a question to talk a little bit more about when Oracle might use a bitmap index. So a bitmap index, unlike a B-tree index, is a single column index. So it can only be used in really two kind of scenarios. I have a where clause predicate on that specific column. And using the bitmap might be the way to get at it. But it's much more commonly used when I have multiple bitmap indexes on a large table and star query transformation is kicking in. What that means is that I will have multiple where clause predicates on that table where I have a bitmap index on each of those columns. Each bitmap index will be used with that where clause predicate, and the result of that bitmap index will be merged with the other results from the other columns to create a single bitmap that I then apply the function to translate that bitmap into a set of row IDs. That's typically when we use bitmap indexes. Again, that could be a whole session in itself about bitmaps and bitmap transformations, but effectively that's when it's used. Either I've got one predicate on one column with one bitmap index, or I have a large number of where clause predicates with bitmap indexes on all of those columns, and then Oracle will use a combination of and or logical operations to join those bitmaps together. Okay, how do we break a really long execution plan? Sometimes the plan runs through pages and it becomes really difficult to read. Okay. So the question is regarding really long execution plans, and is there a way to make it easy and to read? The easiest way I know how to read those plans, unfortunately, is SQL Monitor. It makes it much easier to be able to page down through those. SQL Developer can also be quite useful for this as well. If you take advantage of that tool, that one is free. SQL Monitor, unfortunately, isn't. There is really no great shortcut to this. At least I don't have one. So if somebody does, please share it with me. Typically what I'll do is I'll work from the inside out of those types of queries. Oftentimes I don't need to look at every aspect of the plan. I just need to make sure initially I'm getting the right access methods, the right cardinality estimates, and the right join order. So I'll work from the inside out. So starting with that first table, working my way out. How do I find that first table? Remember, I'm going to get it to display the execution plan with the plus outline in the format parameter. That'll tell me where to start by looking at the leading hint and work my way out from there. Okay, so what kind of indexes do we need for OLAP versus OLTP? The traditional answer for that would be, of course, OLTP use B-tree indexes, OLAP or warehousing use bitmap, but honestly, you can use both. So in both cases, typically bitmaps are less useful in transaction processing, but B-tree indexes can also be useful in a data warehouse depending on your query access method. So if I have a very clean star schema, bitmap indexes would definitely be the way to go, so I can support star query transformation. If, however, I'm working on more of a third normal form in my data warehouse or in my OLAP environment, B-tree indexes may still be useful to me depending on the query access and depending on the cardinality, the selectivity of the indexes that are in that schema. So bitmap indexes typically are more efficient or more performant if I have a few distinct values in that column. But if I have a very unique column or a lot of distinct values, then the bitmap index tends to give us a lot of overhead in that case, and a B-tree index may actually be more efficient. So I know we're out of time. I know there's still a bunch of questions, but in the interest of not wasting people's time, I want to let you guys go on time. But I promise we will definitely share all of the material, including the slides, the recording of this session. And as I said, the little bit that we've missed, I had already planned to do a video next week on the blog for parallel execution. So you'll get access to all of that as well. So with that, I want to thank you all so much for spending all this time with me and for hanging in there for an hour and a half. I hope you found the session useful, and I hope we have an opportunity to talk again soon. Thank you so much.
Thank you very much, Maria. I think you can see a lot of thank you messages in the chat. I think somebody was asking, can we have a full day session with Maria? uh, so thank you very much for covering detailed session on Explain Plan. We really enjoyed. Thanks for your valuable time and support. And by the way, participants, Maria shared many sessions with us. So we'll try to get her time at least one time in a month. So as we requested earlier, you can always thank Maria by using SQL Maria Twitter ID, as you can see in the slide. It is very important to provide a feedback, right? It's not only the speaker feedback. If you want any additional questions, and we will try to send it to Maria by email, and we'll try to get answer, right?
Mhm.
And if you attended all the webinars in the month, please reach out to us. We will send you a participation certificate. Um, so hope you guys are actually scanned this speaker feedback, or you can use the short URL to provide the feedback. And also, I think this Zoom webinar will divert to the speaker feedback. So if you're not able to capture, so the next one. Oh, 1 second. This is what happens. It doesn't go to the next slide. Okay. So who's coming next week? So we have Rob Lockhart. He's an Oracle's director, and he's going to cover Oracle data. It's a database security in cloud. Please watch AIOG website for more details, and also the upcoming webinars. So thank you once again, Maria, for spending your valuable time, and thanks for all the attendees for attending the session. Have a nice day as well as have a nice evening. With that, I'm closing the session. Thank you very much.